Dear viewers, I welcome you to the class 8. I welcome you to the class 8 of heat exchangers. In this class, I'll be explaining you about prerequisites for NTU method. We are done with LMTD method for parallel and counter flow. Now in order to start with NTU method, LMTD method is done. To start NTU method for parallel and counter flow heat exchanger, you need to know about few technical parameters. So the prerequisites for that NTU method, I am explaining it here. This is effectiveness symbol. I will come across each and every parameters. So now initially you need to know the need for this NTU method. Whenever the data is insufficient, that means there is a insufficient data to calculate LMTD, there comes into the picture the method of NTU. Okay, without some data, we can calculate effectiveness with the help of NTU method. So what is the data? For example, you can make a list like outlet temperature of hot fluid, outlet temperature of cold fluid. Even if you don't know the outlet temperatures, even then we can use NTU method. But LMTD is not so, because LMTD, it was theta mean, it was difference of theta 2 and theta 1 by ln of theta 2 by theta 1. Fine. So what was this theta 1 and theta 2? For parallel and counter flow, we have difference. In case of parallel flow, it is THI minus TCI for theta 1, but in counter flow it is THI minus TC naught. In both the cases, these are necessary outlet temperatures to calculate theta mean, right? So here LMTD method fails, we will go with NTU method. I hope you are getting this point. Fine. So whatever I am writing it in blue, it is for your understanding. Whatever it is written in black, that is the actual concept. Okay. So now you need to know 3 dimensionless parameters to start with NTU method. Those parameters are heat capacity ratio or heat capacity rate ratio, represented by C, effectiveness epsilon, number of transfer units, represented by NTU. I'll go with one by one. Coming to heat capacity ratio, that is C, is defined as the ratio of C min by C max. I repeat, ratio of C min, that is minimum value of C, to maximum value of C, C min by C max. So what is this C min and C max? Let us understand that. So this is the definition. For understanding, I am using the blue pen. So now here we know Cp is the specific heat for any fluid. Fine. So now if Cp is multiplied with mass of that fluid, I'll get total heat capacity of the fluid. Fine. So M into Cp is C. Okay. So now let us say this is for cold fluid, so we'll get Cc, and this is for hot fluid, I'll get Ch. Whenever I compare these two, either of the one should be greater. For example, if Cc is greater than Ch, then C min, minimum value of C, and C max is taken like this is greater, so this is maximum, this is less, so this is minimum. Fine. So now here C min by C max is Ch by Cc. On the other hand, if Ch is greater than Cc, then this is minimum and this is maximum, right? Sorry, this is maximum and this is minimum. So this is how C min and C max are taken. So the definition wise, it is the ratio of heat capacity of the fluids to the in such a way we are taking minimum value in the numerator, maximum value in the denominator. This ratio is heat capacity ratio or heat capacity rate ratio, represented by C. This is for your understanding. Is that clear? So now coming to the effectiveness, it is the ratio of Q by Q max. I repeat, it is the ratio of Q by Qmax, where Q is actual. So now here actual heat transfer may be taken as, say, M into Cp of H into change in temperature of H. H means hot fluid, right? Or I can also take that one as cold fluid into change in temperature of cold fluid. Now, for example, if I take parallel flow, higher temperature minus lower temperature, for hot fluid, inlet will be higher, outlet will be lower. Fine. Cold fluid, outlet will be higher, inlet will be lower. It may be for parallel or counter flow, this rule remains same. So these two should be equal in actual practice. Either this or this will be the Q actual. Now what is this Q max? Again for your reference, I am saying Q max is C min into inlet temperature of hot fluid and cold fluid. Now how is this? I'll explain it here. So here we have seen CH and CC. Fine. Let me take this example. CC is greater than CH. For example, here I have got some value like say 12.5, and here I got some value like 8.4. So CH is greater than, CC is greater than CH. That means cold fluid has an ability to receive 12.5 kilojoules of heat, okay, and hot fluid has an ability to give 8.4 kilojoules of heat, right? So this is C minimum and this is C maximum. He is ready to take 12.5, but he is ready to give only 8.4. So what is the maximum value that can be given is this. The minimum value here gives maximum heat flow rate. Even after this, even if the hot fluid gives the heat, he is not ready. He cannot give because it is its ability of that hot fluid to give the heat is only 8.4. Only 8.4 kilojoules of heat can be rejected. There is no excess of heat to be rejected. In that case, even if he is ready to take, there is no one to give. Fine. So this minimum value comes here into picture. So the maximum heat transfer that can be obtained is with the minimum value of C. So we will take this minimum value over here, C minimum. Fine. So now this is the game which is being played at the inlet part itself. At inlet, say cold fluid is going at some 10 degrees centigrade, hot fluid is going at some 20 degrees centigrade. So he is ready to give the heat. So this is the temperature difference. Within this temperature difference, I need to take C min. So it is THI minus TCI. So this is how we will define effectiveness. I repeat, effectiveness is defined as the ratio of actual heat transfer to the maximum possible heat transfer for those fluids, and it is given by Q by Q max. You can have a reference over here. Whatever I have written in blue is for your reference. Now we will proceed with the next one. We have studied with C. We are done with C and epsilon, heat capacity ratio and effectiveness. So the next dimensionless parameter we have is NTU, number of transfer units. So coming to this NTU, number of transfer units, it is defined as the ratio of UA by C min. This equation is NTU. So what is this UA by C min? Let us understand it in literature manner. Okay, this is mathematical one. Let us have some literature analysis for this one. What is this U into A? This is the ability of heat exchanger to transfer the heat. I can say it like heat exchanger's ability to have a heat transfer, to transfer heat. Fine. Heat exchanger's ability is U into A. This is overall heat transfer coefficient. This is EL, area. If I multiply these two, I'll get total value of Q. So that's the ability of that heat exchanger. The C min, this is the minimum ability. Forget about min for a moment. What is the C? Ability of a fluid to transfer the heat, right? Ability of a fluid. So whenever I say C, it is fluid's ability. Fluid's ability to transfer, that means to either absorb or reject. To absorb or reject heat, right? So now if I take this min into an account, minimum into an account, I will say it is fluid's minimum ability to absorb or reject heat. That is C min. Again the same explanation comes over here. I have two different fluids. I'll check with the values. The minimum value I'll be taking. In this case it is CH and in this case it is CC. Likewise I'll be taking the minimum value. So here this gives us the dimensionless number called as NTU. I repeat, NTU is an heat exchanger's ability to transfer heat to fluid's minimum ability to transfer heat. So this is the comparison between heat exchanger and fluid's ability. Fine. So why do we need this? By having this, we'll get some ratio. That means one number. Say I am getting some 250 in one case. In the other case, I am getting 85. So now this for just for reference. Don't go behind this number. It is just for reference. I have taken some number randomly. Okay, this is not like calculated one. So now here number is more, it is NTU is more, here NTU is less. That means here size of the heat exchanger, size of heat exchanger is large, and here the size of heat exchanger is small. So this number NTU gives me the idea, a reference for me to have design parameters regarding its size. I'm sorry, this is the understanding part, so this should have been written in blue. Fine. So higher the number of NTU, larger will be the size of heat exchanger. This is what its physical significance is. Okay, fine. And here significance is, we'll get to know the ratio of C min by C max, which will be used in the further derivations of NTU. And effectiveness is the ratio of Q by Q max. You should be knowing all these three parameters for the derivation of NTU method. Here we will be deriving effectiveness. With the help of effectiveness, we can calculate Q. Okay, it is not direct method to calculate Q. First in first step we'll find out NTU. In second step we'll find out effectiveness. In third step we'll find Q. This is what we'll be doing in the numericals. Okay, finally you need to be clear with the prerequisites. So prerequisites for effectiveness of NTU method in class 8 are its necessity or need, then comes 3 dimensionless parameters C, epsilon and NTU. We'll continue in the next class. Thank you.